So I introduced two of the many possible methods to convert continuous time controller Ks into discrete time controller Kz. One is known as the backward difference method, which is the one in equation 2 here. And the second one is the bilinear method. Okay, so I'm going to first of all, use this example to show how we can actually apply this method to find the discrete time controller. Say the controller I designed in the continuous time is this, okay, hs equals to 1 over s plus 1. And I selected this time interval to be 1, for example, just for the sake of argument. And I want to convert this hs into hz, and then to see how we can actually use hz for implementation in computers. Okay, so select t equals to 1, apply the formula s equals to 1 minus z to the power minus 1 over time t. Substitute that s into here. Okay, t equals to 1, therefore s equals to 1 minus z minus 1. And put that instead of s, I get 1 over, this is s, remember, 1 minus z minus 1 plus 1. So I end up with hz equals to 1 over 2 minus z minus 1. I actually am using a very simple example here, just to illustrate how the conversion works. Okay, so I got here, but that's not end of it. That's only the first step. We have a transfer function for digital controller, but how do we actually convert back into the time domain sequence? What is the algorithms, control algorithms that the computer can use? So we actually need to convert that back into the time domain sequence of control algorithms. Okay, so this is what we need to do. Now think about the controller as, because it's a transfer function between the output and input in Z. So transfer function between output and input. Let's assume my output is YZ, my input is XZ. Okay, and the transfer function is that. Now the next steps is very similar when we try to find differential equations from transfer functions. What I do here is that I'm going to multiply yz into the denominator terms of the transfer function in z. That equals to xz multiplied into the numerator terms of the transfer function. So yz times the denominator terms, that's yz times 2, minus z to the power minus 1 times yz. And make sure you leave the output on the left-hand side. Okay, that equals to 1 times xz. Now I'm ready to apply that inverse that transform. xz will correspond to xn. It's a bit like xs correspond to xt. yz correspond to yn. So it's 2 times yn. This, if yz correspond to yn, yz times z minus 1. Z minus 1 is the delay of one interval. Therefore, this second term on the left-hand side becomes yn minus 1. That's a delay of one interval. The next thing you need to do is to reorganize that equation, put everything else onto the right-hand side except yn, that's output, which will give me an equation like that. So if I move this to the right-hand side, it becomes xn plus yn minus 1 divided by 2. This is the algorithm that you can use to implement the controller in the computer. It's basically you use a software instruction to write this equation down. So that says for any output, at this any time instant or sampling instant n, you take the input at this interval. You take the input from you take the output from the previous interval, which is you calculated last time. Divide that by 2. That's the update for your current output. Okay, so the process is quite simple there. So in this case, for any time instant, because if you just imagine your head, you have time sequences. So you have different interval times for the computer to come back, do the processing or do the calculations. So at any particular time, because they are divided into different sections, for any time you can take in the current input, ask A to D converter to say, I want a value now for your input. And then you say, right, what is the output value I calculated before? And add them together, divide by that too. This will be saved in the memory. So every time you do this, you save that in memory. So after you've done that, you find yn, you save that to the memory as well. So that when the next interval comes, you use this as the previous one. Okay, you might say, well, where did my previous come from? Well, that previous calculations you've done that, but you start when you first start it. Of course, you don't have that value, but when you first start, everything will be 0. We are assuming that we're starting from a 0 status. Nothing happens. Okay, before t equals to 0, there's no value there, so you start from 0. And then afterwards, every time you go over one step, the clock says, do the calculation now, do the calculations now. You say, right, what's my current input? What's the value I saved last time? Add them together, divide by 2. And then you need to save in your software instruction, you need to save the current output. So when the next time comes, this will be your previous output. So the process is quite straightforward. If I use the bilinear method for the same transfer function, in continuous time is 1 over s plus 2. I use this formula for the bilinear transform. T is 1, so it's 2 over t, that's 2 over 1. 1 minus z minus 1 over 1 plus z to the power minus 1. So multiply that 2 by this. And then you replace that s in equation 1 by equation 3. So this goes into here. So that becomes 2 times 1 minus z minus 1, and 1 plus z minus 1, then plus 1. Of course, we need to, because there's now, it looks like quite complicated form. There's fraction inside fractions. So we need to simplify that. So what I do, I can just multiply a numerator denominator, same numerator denominator to here. And this 1 plus at the bottom, 1 plus z minus 1 will cancel that out. So this becomes, this first term becomes 2 times 1, 2 times minus z minus 1, and then this 1 times that, this becomes 1, this becomes z minus 1. So add the two terms together, you get 3 minus z minus 1. On the top is 1 times that, which will give you 1 plus z to the power minus 1. So that is a transfer function we can get from the bilinear transform method. Okay, so different conversion method will give us different transfer functions. Now, if we want to implement that, again, remember the transfer function, whether it's for continuous or for discrete time, it's the output divided by input in frequency domain. So it's yz over xz. So do a cross multiplication. Yz multiply into the denominator terms of the transfer function. That will give me 3y minus z minus 1 times yz. That equals to input multiply into the numerator terms. That will give me xz plus xz z minus 1. Apply inverse Z transform to that. Xz will give me xn. Xz times z minus 1 is the delay of xn, therefore it is xn minus 1. Yz is yn. Yz times z minus 1 is yn minus 1. It's a delay of that. Okay, a previous value. Reorganize that. Leave the only yn on the left hand side. Okay, so move this to the right hand side, it becomes plus yn minus 1, and then divide 3 to both sides, and you end up with equation number 9, which is xn plus xn minus 1 plus yn minus 1 divided by 3. Now, if you're going to write a software code to implement that in a computer, what you need to say, right, when the clock comes, say, right, computer, wake up, you want to do the calculations now for the output. What you need is to say, okay, I need to take in the current input from my A to D converter. I need to remember somewhere in my memory space, I need to take the previous input, the input at the previous time interval, and I also need a value from previous output, the value I calculated last time. Add them together, divide by that 3. That will be my current output. Then you will need to save the current input and the current output somewhere in the memory, so that when the next time the interval comes, this xn and yn becomes xn minus 1 and yn minus 1. That will be your previous input and output. So in this case, your computer will need one more memory space to remember the previous input. Okay. Now, so I have the continuous time controller 1 over s plus 1. I have the discrete time controller using the backward conversion method, okay, with this backward difference method, which is this one, and I also have the controller using the second conversion method, that is the bilinear transform method. And you might wonder, what's the difference between the 3? What's their impact on the control system? You end up with all 3 different forms. So one of the ways to check is actually try to look at their frequency response. Okay, so over here I use MATLAB to produce the frequency response or frequency bulk diagrams for me. In the red line, okay, the dotted red line is the frequency response of my continuous time. This is the one I designed for, okay, so I use design method to get that transfer function. The blue line is the one that's converted use the backward. The green line is the one frequency response we design with the bilinear method. So if you compare the 3 between the two, the blue line starts to get different from the red at a fairly low frequency, whereas the green line actually sticks to it until you get somewhere there. Okay, but at higher frequencies, it is the green line that's much different. Okay, this line there is a half of the sampling frequency. Okay, it's this line there, this frequency is half the sampling frequency. Digital systems are not capable to deal with anything than half of the sampling frequency. Therefore, that's why the frequency response stops here. continuous time does not stop here. Okay. So now, so for the two conversion methods, the green line is much better at lower frequencies, and the blue line, the backward method, is slightly better, or it's better at high frequencies. But we are talking about practical terms, and in practice, our sampling frequency is a lot higher than we would need, or than the highest frequency we'll deal with. Remember this 100 times, I said. So in reality, your control system will mostly operate at lower frequencies. Therefore, under these circumstances, the bilinear method will give you a better representation of the continuous controller. Now, same argument goes for the phase plot. You can see there, this is actually a quite clear cut, because the bilinear will give you a much closer match to the continuous time, whereas the blue in backward method is quite different. Okay, so the bilinear method in general works better at low frequencies, and they give you better representation of the continuous time, but it is slightly more complex than the backward method. So that was an example of what we can do with either backward difference or bilinear transform method. Now, in general, if you have a transfer function in Z after you've done the conversion, the steps to derive the control algorithms is through the cross multiplication. So here we have this very general form. Okay, it's a second order controller, and the transfer function for the Z is, in the numerator, I have a plus b z minus 1 plus c z minus 2. In the denominator, I have 1 plus d z minus 1 plus e to z minus 2. Now, a, b, c, d, e are constant. These are basically our control gains. Okay, and what you do as a rule is to do a cross multiplication between numerator and input. This time I change the input to u. It really doesn't matter. Okay, output y multiply into the denominator terms. Then you equal to 2. Then you apply inverse Z transform. Reorganize that equation, because Z minus 1, Z minus 2, Z minus 1, Z minus 2 are easier to deal with, because this will just becomes yn minus 1. This will become yn minus 2. This will become u minus n minus 1. This will become u z minus 2. Then every single z to the power minus 1 represents a delay. So once you get here, and then you reorganize it, you leave the current output yn on the left-hand side, move everything else onto the right-hand side. Then you have a form that you can use to write your software code. That's, I showed that in my previous example, and I just wanted to give you a general rule for converting from KZ into the form that you can use in time domain to write software code. So there are two steps there. One is to convert from KS to KZ. Second step is from KZ to get into the time form yn. Okay, because KZ is yn yz over uz. Okay, transfer functions. And so we need to get to this. We need to get to this in order to actually write the code. This one doesn't give you the code. Okay. So I'm giving you another example here. This time I'm not going to get too complicated with the conversion. So this is a GS. It's an example I used before for the design of phase need compensator. Okay, the plant, the object for control, is defined by the transfer function gs, which is 1 over s times 10s plus 1. The controller we ended up with, using the frequency domain, the both plots, the crossover frequency, the phase margin, that kind of criteria, we use this to design a controller. We get this equation 2. Now, GS is a plant. You don't convert that. That represents your satellite radar or satellite tracking radar. Okay, that's not a digital system. It's a moving object, or the angle of that radar changes with time. Okay, it is the controller that we need to convert if we want to implement that in digital form. Okay, so I use two methods here. One is the backward difference. The other one is the bilinear transform method. So backward difference is 1 minus z minus 1 over t. Bilinear method is s equals to 2 over t, 1 minus z to the power minus 1 over 1 plus z minus 1. If I choose the sampling interval to be 0.4, so this will become 1 minus z minus 1 over 0.4. This would be 2 over 0.4. Okay. I replace s into this s into this s and that s. I end up with this equation. Replace this into equation 2, this s and that. I end up with that equation. Put t values into there. I get two transfer functions. K1 comes from the backward difference method. K2 comes from the bilinear method. Okay, skipped the intermediate steps because it's something that you can do. It's simple replacement of s values and then rechange the format. And from there, you can actually find the algorithms as well, because I can do, for the backward difference, I can do a cross multiplication and end up with the transfer function, with the actual control algorithms like that. Okay, multiply yz into the denominator, multiply uz into the numerator, and then you do an inverse z transform, reorganize it, leave the yn on the left-hand side. Same approach for the bilinear method, and you end up with yn equals to this. Okay, that's how you implement it. Now, to assess the performance of the different approaches, and I've actually resorted to computer simulations to give me some indication of how well or how poorly they behave. So what I've done here, so I put the plant, the GS into here. I'm not changing anything. It's not digital. I'm not converted it. Okay, so the plant is GS, and I put my KS that I design in continuous time. The phase need compensator I designed in continuous time in my previous discussion, and I put a feedback there, and I put a step signal to it to study the step response of that system, of the continuous time system. I copy the same plant down here, but I use digital controller 1, which is the one I used backward difference method to convert from continuous to here. So this is a conversion from the continuous using backward difference method. And then I also copy the plant down. That, again, it's a GS, not GZ, okay? It's GS, I copy that down, and I created another controller that's to implement the controller I converted from continuous time to digital time, a digital system with the bilinear method. Again, in both cases, I put a step in there, and I connect the feedback there, and then I put some scopes as an output to see how the system responds, so I can compare their performances. That's what I get. The continuous time is the one in red. Digital 1 That's the digital controller using the backward difference method. The green one is the one from digital 2, which is from the bilinear method. So you can see there, the bilinear method can give you a better performance or closer to the continuous controller. And the blue line is a backward difference. Now, in any case, digital controllers, they are not really doing anything better in terms of theoretical performances than the continuous time controller. That is really not what we are doing with why we are using digital controllers. Okay, we don't expect digital controller to perform or behave better than the continuous time. The advantage of using a digital controller is that it's not easy to implement, because you're writing software code rather than building electrical circuits. Electric circuit is normally what you need for implementing continuous time controllers. And also, we don't have to change the circuit. If we need a retuning of the control or redesign a controller, all you need to do with digital control is to change the software code. That is a lot easier thing to do than change the circuit design. And it will save money, it will save time. It gives you a lot more flexibility. It is particularly true when you have very complex control algorithms. And also the algorithms that requires change with time. So the kind of adaptive nature of things, it's easier for the software, the code to change rather than designing an electrical circuit for that purpose. So digital systems or digital control systems do have their advantages. And that's why nowadays people go for digital systems. You know, if you look around all the electronic gadgets you have, they're all digital because they give you extra flexibilities. And in terms of noises processing, it is better as well because they use zeros and ones. It gets less interfered by noise, external noises. Okay, so I've done 2 sessions for this part, but I only have 1 set of practical questions for you. Okay, so make sure you actually go and do them. And I have some transfer functions here from the continuous time, and I want you to convert them into the discrete time transfer function, and then get to the control algorithms using the 2 steps in my examples. Okay, using either backwards or both actually, backward difference method and bilinear method. Over here, I selected the sampling interval for you. Okay, so t equals 0.1. Thank you.